Welcome to this session where we'll solve LeetCode problem number 1101, titled The Earliest Moment When Everyone Becomes Friends. In this problem, we aim to determine the earliest timestamp where all individuals in a connected network can be considered friends. Let's dive in and explore the solution step by step. In this problem, we have a social network consisting of n people, labeled from 0 to n1. We are given a list of logs, where each log is a triplet containing a timestamp and the identifiers of two people who became friends at that time. The goal is to determine the earliest timestamp when the entire network becomes connected. Friendship in this problem is symmetric, meaning if one person is friends with another, the reverse is also true. Additionally, each person is trivially considered friends with themselves. The network is defined as connected if there is a path of friendships connecting any two individuals. If it's impossible to connect the entire network, we return -1. The input includes the list of logs and the integer n, representing the total number of people. The output of the problem is a single integer, representing the earliest timestamp when everyone in the network becomes connected. If the network is never fully connected, the output should be -1. To clarify this further, let's look at an example. We are given a set of logs and n equals 6, meaning there are 6 individuals. Initially, all 6 people are isolated. At 20190101, 0 and 1 become friends. This represents the first step toward building connections within the network. After that, at 20190104, 3 and 4 become friends, forming another small group. Then, at 20190107, 2 and 3 become friends, which expands the group of 3 and 4 into a larger group containing 2, 3, 4. Moving forward, at 20190211, 1 and 5 become friends. At this point, there are still multiple disconnected groups. While 2 and 4 are already part of the same group, at 20190224, no new connections are formed. Finally, at 20190301, 0 and 3 become friends, which unites all the groups into one fully connected network. The earliest timestamp when everyone is connected is therefore 20190301. Now, consider a simpler example where n equals 4 and the logs indicate connections at timestamps 0, 1, and 2. At timestamp 0, 0 and 1 become friends, forming a small group. At timestamp 1, 1 and 2 become friends, expanding the group to 0, 1, 2. Finally, at timestamp 2, 2 and 3 become friends, which connects all individuals into one group. This means the earliest timestamp when the network becomes fully connected is 2. However, in another example, if the logs only record connections at timestamps 0 and 1, but the connections form two separate groups, the network remains disconnected. In this case, there is no way to connect everyone, so the output would be -1. The constraints of the problem include a minimum of 2 and a maximum of 100 people in the network, and up to 10⁻4 logs. Each timestamp is between 0 and 10⁻9, and the individuals in each log are distinct. Logs may not be given in order, so it's important to process them correctly. Several edge cases need to be considered, such as when there is only one log and the network becomes connected immediately, or when the logs are insufficient to fully connect the network, resulting in an output of -1. Additionally, even if the logs are unsorted, processing them in order of their timestamps is crucial. Finally, scenarios with multiple disconnected components should also return -1. To solve the problem, we can use the union find or disjoint set union data structure to efficiently track connected components. The steps are as follows. First, sort the logs by timestamp. Then, for each log, merge the groups of the two individuals involved using the union operation. As we process each log, we check if all individuals are part of a single connected component. If this happens, we return the current timestamp. If we process all logs without achieving full connectivity, we return -1. This approach ensures that we can handle the problem efficiently, even for large inputs, by dynamically merging groups and checking connectivity as we go. To solve problem number 1101, the earliest moment when everyone becomes friends, we need to determine the earliest point in time when all individuals in a social network are fully connected. The problem can be thought of as a dynamic connectivity problem in a graph, where nodes represent individuals and edges represent friendship events. One approach to consider is brute force. Here, every friendship event is treated as an edge, and after adding each edge, we repeatedly check if all nodes in the graph are connected. This can be achieved using methods like BFS or DFS. However, the drawback is its inefficiency, as verifying connectivity for each event repeatedly results in a high time complexity of O, M*, V plus E, making it impractical for larger datasets. A more efficient approach is using an optimized union-find data structure, which avoids traversing the graph repeatedly. With union-find, we can manage dynamic connectivity by representing individuals as groups, where friendships merge these groups until only one group remains. This makes the process far more efficient and scalable. In the optimized union-find approach, the logs are first sorted by timestamp to ensure that friendship events are processed in chronological order. Then, as each event is processed, groups are merged using union operations. We track the number of connected components, and the process stops as soon as all nodes are part of a single connected component. Sorting the logs has a time complexity of O, M log M, and each union or find operation has an amortized time complexity of O, alpha, N, where alpha, N, is the inverse Ackermann function, which grows extremely slowly and can be considered nearly constant. This results in an overall time complexity of O, M log M plus M asterisk alpha, N, making it far more efficient than the brute force approach. Additionally, this method is memory efficient. While it requires an understanding of union find, which may be challenging for beginners, its speed and scalability make it highly suitable. Another alternative is Kruskal's algorithm, which is conceptually similar since it also uses union find to check connectivity. However, Kruskal's algorithm is more focused on constructing a minimum spanning tree, and in this problem, we are only concerned with the earliest timestamp when the graph becomes connected, not minimizing costs. The chosen strategy for this problem is the optimized union find approach because it provides the best balance between efficiency and simplicity. The key insight here is that by sorting the logs by timestamp, we can process the events in the exact order they occur, which aligns perfectly with the goal of identifying the earliest moment of complete connectivity. Union find handles dynamic connectivity efficiently by merging groups and tracking the number of connected components, avoiding the need for redundant graph traversals. Thanks to its amortized near-constant time complexity for union and find operations, this method is highly scalable, even for large inputs. The aha moment in this problem is realizing that it can be reduced to a dynamic connectivity problem, a perfect fit for union find. By simply tracking the number of connected components, we can determine exactly when the graph becomes fully connected without any unnecessary computations. When comparing the approaches, each has its trade-offs. The brute force approach is straightforward and easy to understand but becomes computationally expensive as the input size grows, making it unsuitable for larger datasets. Kruskal's algorithm, while efficient, is less intuitive for this problem since it is typically used for minimizing cost in a graph rather than finding a specific timestamp. On the other hand, the union find approach strikes the right balance. It is efficient, with a time complexity of O, M log M plus M asterisk alpha, N, and scalable, making it well suited for this problem. While it may require a deeper understanding of the union find data structure, its clarity, performance, and alignment with the problem's requirements make it the ideal choice. This balance of simplicity and efficiency is why it stands out as the best solution for this problem. To solve this problem, we need to determine the earliest point in time when all individuals in a group of n people are connected. The input consists of logs that record friendship events, where each log specifies the timestamp and the two people who became friends at that moment. This can be represented as a dynamic connectivity problem, where individuals are nodes in a graph, and friendship events create edges between these nodes. The goal is to find the first timestamp at which all nodes belong to one connected component. To efficiently track and update these connections, we use the union find data structure, also known as disjoint set union or DSU. It supports two main operations: find, which identifies the representative of the set containing a given node, and union, which merges two sets. Union find is particularly suitable for this problem because it can dynamically update connectivity information with an amortized time complexity that is nearly constant. To begin, the algorithm requires sorting the logs by their timestamps in ascending order. This ensures that we process events in chronological order, as earlier events might affect the connectivity of subsequent ones. Once the logs are sorted, the next step is to initialize the union find structure. We create a parent array where each node is initially its own parent, representing isolated components. Additionally, we can use a rank array to optimize the union operation by always attaching smaller trees under larger ones. We also introduce a count variable, set to n, which keeps track of the number of connected components. Initially, each node is its own component, so count equals the total number of nodes. Next, we process each friendship event in the sorted logs. For each log, we perform a union operation on the two individuals involved. If the union operation successfully merges two previously separate components, we decrement the count variable. This is because every successful merge reduces the number of disconnected groups. After each union operation, we check whether count has reached 1, indicating that all nodes are now in a single connected component. If this condition is met, the current timestamp is returned as the earliest moment of full connectivity, as it represents the first point in time where all individuals are part of the same network. If the loop completes and count never reaches 1, we return -1. However, this scenario is unlikely given the problem constraints, which typically ensure full connectivity is possible. There are several key insights that make this algorithm efficient. First, sorting the logs by timestamp is essential for correctness, as processing events out of order could lead to inaccurate results. Second, the union-find data structure is highly efficient, especially with optimizations like path compression and union by rank, which ensure that operations are nearly constant time. Finally, the algorithm takes advantage of an early stopping condition. As soon as all components are connected, we terminate the loop, avoiding unnecessary calculations. For example, consider the input with n equals 4 and logs containing timestamps in pairs of individuals who become friends. After sorting the logs, we process each event sequentially, updating the union-find structure and monitoring the count variable. In the example, we begin with the union-find structure initialized as parent equals 0, 1, 2, 3, and count equals 4, since each node is its own component. Processing the first log, 2019010101, we perform a union operation between nodes 0 and 1, reducing count to 3. Next, the log, 2019010434 merges nodes 3 and 4, further reducing count to 2. Then, the log, 2019010723 merges nodes 2 and 3, resulting in count reaching 1. At this point, all nodes are connected, and we return the timestamp 20190107 as the earliest moment of full connectivity. The algorithm is efficient, with the time complexity dominated by the sorting step, which is O, k asterisk log, k, where k is the number of logs, and the nearly constant time union-find operations. The space complexity is O, n, as the union-find structure requires storage proportional to the number of nodes. To ensure the algorithm handles all possible scenarios, we must consider edge cases. If there is only one individual, n equals 1, the graph is trivially connected, and we return 0 immediately. Another edge case is when the logs are insufficient to fully connect all individuals. In this situation, we return -1. Additionally, duplicate friendship events may occur, but the union-find structure naturally handles these by avoiding redundant unions. These considerations ensure the algorithm is robust and performs correctly under various conditions. Here, we start by defining a union-find class, which will help us efficiently manage the connected components of the network. The constructor initializes 3 attributes: parent, which is a list where each node initially points to itself as its own parent; rank, which tracks the depth of the trees for union by rank optimization; and components, which keeps count of the total number of connected components, starting with the given size. Next, the find method is implemented using path compression. This ensures that when we look for the root of a node, we also flatten the structure by pointing the node directly to its root, which speeds up future lookups. Then, the union method is defined to merge two sets. It uses the find method to get the roots of the nodes, and if the roots are different, it attaches the smaller rank tree under the larger rank tree to keep the structure balanced. If the ranks are equal, one root is chosen arbitrarily, and its rank is increment. Finally, the number of components is decrement whenever two sets are successfully merged. Now, we move to the solution class, where the earliest ACT method is defined. This method takes in the logs of interactions and the number of people, n. First, we create an instance of the union-find class, passing n as the size. Then, we sort the logs by their timestamps to ensure we process the events in chronological order. Next, we loop through the sorted logs, extracting the timestamp and the two people interacting. For each interaction, we call the union method to connect the two people. If the number of connected components drops to 1, meaning everyone is in the same connected group, we return the current timestamp as the earliest moment when everyone became friends. If the loop completes and not all people are connected, we return -1 to indicate that it is not possible for everyone to become friends with the given interactions. Here, we start by defining a union find class, which is a common approach to solve connectivity problems. The class uses two main arrays, parent to track each node's leader and rank to optimize the union operation. We also have a components variable to keep track of the number of connected components. In the constructor, we initialize these arrays. Each node is its own parent initially, and all ranks are set to 1. This means every node starts as an independent component. Then, we implement the find method, which determines the root of a node. To optimize future queries, we use path compression here, so that nodes point directly to their root. This reduces the time complexity of subsequent operations. Finally, we begin the union method, which will connect two nodes by linking their roots together. In the union method, we first find the roots of the two nodes. If the roots are different, it means the nodes belong to separate components, so we proceed to connect them. To maintain efficiency, we use union by rank. If one root has a higher rank, it becomes the parent of the other, ensuring the tree remains shallow. If the ranks are equal, we arbitrarily choose one root to be the parent and increment its rank. After performing the union, we decrement the components count, as we've successfully merged two separate groups into one. This ensures we're accurately tracking the number of connected components. With this, the union find class is ready to efficiently manage the dynamic connectivity of nodes. Now, we move to the solution class, which solves the problem using the union find structure. In the earliest stack method, we first create an instance of union find with n, the total number of people. We then sort the logs array by timestamp to ensure we process the events in chronological order. Next, we iterate through each log entry. For each log, we extract the timestamp and the two people involved. We use the union method to connect these two people. After each union operation, we check if all individuals are now connected by calling getComponents. If the number of components is reduced to 1, we return the current timestamp, indicating the earliest moment everyone became friends. If we finish processing all logs and still have more than one component, we return -1, as it means not all individuals can be connected. We are given a list of logs representing events where two people became friends, and our goal is to determine the earliest time when everyone is connected. For the first example, we start with 6 individuals labeled from 0 to 5. To solve this, we use a union find data structure. Initially, each person is their own parent, so the parent array is 0, 1, 2, 3, 4, 5, and the rank array is 1, 1, 1, 1, 1, 1. The number of components, or groups of connected people, is 6. The next step is to sort the logs by their timestamp. Once sorted, we process each log in chronological order. The first log, 20190101001, tells us that persons 0 and 1 became friends. Using the union find structure, we perform a union operation, connecting these two nodes. After the union, the parent array becomes 0, 0, 2, 3, 4, 5, the rank of node 0 increases to 2, and the number of components decreases to 5. The next log, 201901043, 4, indicates that persons 3 and 4 became friends. Performing the union operation connects these two nodes, resulting in the parent array 0, 0, 2, 3, 3, 5, the rank of node 3 increases to 2, and the components count decreases to 4. The log 201901072, shows that persons 2 and 3 became friends. After processing this log, nodes 2 and 3 are connected, giving us the parent array 0, 0, 3, 3, 3, 5, and reducing the components count to 3. For the log 20190211115, persons 1 and 5 become friends. After this union, the parent array updates to 0, 0, 3, 3, 3, 0, and the components count drops to 2. The log 201902242, 4 involves nodes 2 and 4, but they are already connected, so no changes occur. Finally, the log 201903010, 3 connects persons 0 and 3. The union operation results in the parent array 0, 0, 3, 0, 3, 0, the rank of node 0 increases to 3, and the components count becomes 1. At this point, everyone is connected, so we return the timestamp 201903001 as the earliest moment when all individuals became friends. In the second example, we are given 5 individuals labeled from 0 to 4, and a shorter list of logs. Initially, the parent array is 0, 1, 2, 3, 4, the rank array is 1, 1, 1, 1, 1, and the number of components is 5. The logs are already sorted by timestamp, so we proceed to process them. The first log, 201901010, 1, connects persons 0 and 1. After the union, the parent array becomes 0, 0, 2, 3, 4, the rank of node 0 increases to 2, and the components count decreases to 4. The second log, 201901041, 1, 2, connects persons 1 and 2. After this union, the parent array updates to 0, 0, 0, 3, 4, the rank of node 0 increases to 3, and the components count drops to 3. The third log, 201901073, 3, 4, connects persons 3 and 4. After processing this log, the parent array becomes 0, 0, 0, 3, 3, the rank of node 3 increases to 2, and the components count decreases to 2. At the end of processing all logs in example 2, we observe that the number of components is still greater than 1. This means not everyone is connected, and it is impossible to determine a single timestamp when all individuals became friends. As a result, we return -1 to indicate that it is not achievable with the given logs. In the third example, we have the smallest possible input, 2 individuals labeled 0 and 1, and a single log entry. Initially, the parent array is 0, 1, the rank array is 1, 1, and the components count is 2. The logs are already sorted, so we process the only log, 1, 0, 1, which connects persons 0 and 1. After performing the union operation, the parent array updates to 0, 0, the rank of node 0 increases to 2, and the components count becomes 1. Since all components are now connected, we return the timestamp 1 as the earliest moment when everyone became friends. To analyze the time complexity of our solution, we break it down into 2 main components, sorting the log entries and performing union find operations. First, the logs are sorted by their timestamps using Python's built-in sort function, which has a time complexity of O, m** log m, where m represents the number of log entries. This ensures the logs are processed in chronological order. Next, we perform union find operations for each log entry. For each union operation, we need 2 find operations to identify the roots of the nodes being connected. With path compression and union by rank, the amortized time complexity for a single union or find operation is O, alpha, n, where alpha is the inverse Ackermann function. Although alpha, n, grows incredibly slowly and is nearly constant for practical purposes, the total time for all union operations across m logs is O, m** alpha, n. These 2 steps together form the backbone of our time complexity analysis. Now, combining the time complexities of sorting and union find operations gives us the overall time complexity of the solution. Sorting the logs contributes O, m** log m, while the union find operations contribute O, m** alpha, n. Since alpha, n, grows extremely slowly and is effectively constant for typical input sizes, it becomes negligible compared to log m. Therefore, the overall time complexity simplifies to O, m** log m. Moving on to space complexity, we account for the union find data structure and any auxiliary space used during sorting. The union find structure requires space for 2 arrays, the parent array and the rank array, each of size n, where n is the number of people. This contributes O, n, to the space complexity. Sorting the logs may also require auxiliary space, depending on the sorting algorithm. In Python, timsort, the default sorting algorithm, requires O, m, space in the worst case. Thus, the total space complexity depends on both n and m. The overall space complexity combines the contributions from the union find data structure and the sorting auxiliary space. This gives O, n plus m as the total. However, in most scenarios, the number of people, n, is significantly smaller than the number of logs, m. As a result, O, m, becomes the dominant term. Next, we turn to best, average, and worst-case scenarios. In the best case, all people could become friends early in the log, potentially after the first few entries, leading to fewer union-find operations. However, sorting still dominates, so the time complexity remains O, m asterisk log, m. On average, we process most of the logs, and the time complexity again is O, m asterisk log, m. In the worst case, all logs are necessary to connect everyone, and while union-find operations add minimal overhead, the sorting step still dictates the overall complexity, which remains O, m asterisk log, m. To better understand the efficiency of the union-find approach, let's compare it to a naive method. A naive approach might involve checking connectivity after processing each log entry. Using BFS or DFS, this would take O, n plus m, for a single check. Repeating this for all m logs results in an overall time complexity of O, m asterisk, n plus m, which simplifies to O, m times n plus m squared. This is significantly worse than the union-find approach. In contrast, the union-find method optimizes connectivity checks to O, alpha, n, per operation, thanks to path compression and union by rank. Combined with the O, m asterisk log am cost of sorting, this approach is far more efficient, especially for large datasets, making it the preferred method for solving this problem. The efficiency of the union-find approach is backed by its mathematical properties. Path compression ensures that the tree structure becomes flatter with each find operation, speeding up subsequent operations. Union by rank ensures that the tree remains balanced, preventing it from growing too tall. Together, these optimizations guarantee that performing m union-find operations has a total time complexity of O, m asterisk alpha, n, where alpha, n, is nearly constant for practical inputs. With sorting dominating the overall complexity, the final time complexity of the solution is O, m asterisk log, m. The space complexity, which accounts for both the union-find data structure and sorting, is O, n plus m. This combination of time and space efficiency highlights the strength of the union-find approach for solving this problem. When solving this problem, there are a few common mistakes you should watch out for. First, it's critical to sort the logs by timestamp before processing. Since the friendship events occur over time, processing them out of order can lead to incorrect results. For example, later friendships may incorrectly influence the state of earlier ones. Next, mistakes in implementing the union-find algorithm are another frequent issue. Without optimizations like path compression and union by rank, the performance of union-find can degrade significantly, resulting in operations that take linear time instead of nearly constant time. This can be especially problematic for large datasets. Another pitfall is failing to handle edge cases, such as when the number of people, n, is 1 or when the logs list is empty. These scenarios might seem trivial but can easily lead to runtime errors if not accounted for. Finally, some solutions mistakenly assume that all nodes are connected at the start, which overlooks the need to actively track the number of connected components as the logs are processed. These assumptions can lead to incorrect results or missed conditions in your code. Another common inefficiency is repeatedly checking whether all nodes are part of the same connected component by iterating through the entire graph. This is unnecessary and inefficient. Instead, you can maintain a count of connected components and simply decrement it as nodes are merged. Once the count reaches 1, you know everyone is connected, allowing you to stop early. From an interview perspective, it's important to recognize that this problem is fundamentally about graph connectivity. Be prepared to thoroughly explain how union-find works, specifically emphasizing its optimizations like path compression and union by rank. A common follow-up question might involve adapting your solution to handle dynamic changes, such as when connections are added or removed after the initial logs are processed. Interviewers also often focus on the efficiency of your solution, so highlight the nearly constant time complexity of union-find operations, which makes it well-suited for handling large datasets. Finally, identify the broader pattern. This problem is closely related to connected components and minimum spanning tree problems in graph theory, so recognizing this can help you approach similar challenges more effectively. This problem is closely related to several other graph-based problems, so practicing them can deepen your understanding of the underlying concepts. Examples include LeetCode number 323, which focuses on counting connected components in an undirected graph, and LeetCode number 547, which is about determining the number of provinces, a variation of the connected components problem. Similar problems include LeetCode number 684, which asks for the redundant connection in a graph, and LeetCode number 200, which involves finding the number of islands in a grid. In terms of alternative approaches, UnionFind is the optimal choice for this problem due to its efficiency, with a time complexity of n log *n, where log *n is the inverse Ackermann function. However, it does require additional memory to maintain the parent and rank or size arrays. If you're not using UnionFind, depth-first search or breadth-first search can also work. These methods have a time complexity of n plus e for each traversal, where e is the number of edges. While they are simpler to implement, they are less efficient for dynamic scenarios where graph structure changes over time. Another alternative approach to solving this problem is using Kruskal's algorithm, which is often used for finding minimum spanning trees. In this context, you would treat the logs as edges of a graph and sort them by timestamp. The algorithm then processes each edge in sorted order, using UnionFind to determine when all nodes are connected. The time complexity of Kruskal's algorithm includes e log e for sorting the edges and e log *n for the UnionFind operations. While effective, the overhead of sorting edges can make this approach less efficient, especially when the graph is sparse. This trade-off is worth considering when comparing Kruskal's algorithm to other methods like UnionFind or BFS/DFS. Each approach has its strengths, so understanding their trade-offs will help you make informed decisions depending on the specific constraints of the problem you're solving. Great work! We've successfully solved LeetCode problem number 1101 using UnionFind and discussed its complexity. Remember, understanding dynamic connectivity concepts can be extremely useful in interviews and real-world applications. Thank you for watching, and I hope to see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!